Good morning, everyone. Today we are going to see about the Smith chart. Generally, the Smith chart is a graphical tool that is used to visualize, analyze, and solve the problems related to the transmission line and impedance. That is, it provides a convenient way that is used to represent a complex impedance, reflection coefficient, admittance, and a single chart. You have already learned about Smith chart in control system itself, right? So instead of performing a lengthy calculation, engineers can use a Smith chart to visualize the impedance transformation, and it is used to determine the reflection coefficient, and it is used to calculate the VSWR. VSWR is nothing but voltage standing wave ratio. And it's used to design matching networks quickly and accurate. Why this Smith chart is used? It's used to find a impedance matching condition. It is used to find reflection coefficient. It is used to determine VSWR. VSWR is voltage standing wave ratio. It is used to determine return losses. Okay. It's used to analyze the transmission line behavior. If, if the if the signal is transmitted in a network, the entire signal will be transmitted means the impedance will be perfectly matched. If it is not imperfectly matched means the part of the signal will be reflected back to the source itself. So there will be some losses in the network. So here ZL is the load impedance and Z0 is the source impedance. Okay. And this is a gamma is a reflection coefficient. Next, we are going to see about the key features. Generally, the Smith chart is a graphical representation of the complex reflection coefficient, that is a gamma. So used to display the impedance and admittance. It contains a constant resistance and reactance circle, and it provides a quick graphical solution for impedance matching and transmission line analysis. Okay, these are the key features of Smith chart. And let us see the purpose and application of Smith chart. What are the applications of Smith chart means? So use it to find the analysis of transmission line. That is, Smith chart is used to analyze the behavior of transmission line, including impedance transformation, standing waves, and signal reflection. For in real-time example, in a cable TV network, the signals will be travel to the long coaxial cable, right? So engineers can use a Smith chart to analyze the impedance changes and minimizes the signal losses over a transmission line. Okay. Then impedance matching. Impedance matching, this is one of the most important applications of the Smith chart, is the impedance matching between source and load. In order to ensure that is the maximum power will be transferred to the load. So, for example, in a Wi-Fi router, the antenna impedance that must be properly matches with the transmitter impedance will be matches with the receiver impedance. So, it is a perfectly matched. That indicates it is a the impedance will be properly matched. Then it's used to find a reflection coefficient visualization. Generally, the Smith chart usually represents a reflection coefficient, that is a gamma. It make it is easy to determine how much signal is reflected due to the impedance mismatch. Okay. Then the real time example is that in a mobile phone antenna, that is engineers use the Smith chart to check a antenna matching. Okay. Then the practical applications are, that is, it's used to design the antenna. That is, a Smith chart helps to design and tune the antennas for properly impedance matching it. And it will, that is, the efficiency will be calculated. That will be a maximum. If it is a properly matched, then the efficiency will be a maximum. Okay. For example, Wi-Fi antennas, smartphone antennas, satellite communication system, etc. The benefit is that it improves the signal strength and communication range. Then, circuit design. RF engineers use the Smith chart to design amplifiers, filters, and matching the networks. It helps, that is, in order to avoid a lengthy calculation, the Smith chart is very useful to calculate the impedance and admittance of a network. Okay. Then, it is used to find a RF system verification. That is, We have already learned about vector network analyzer, right? So VNA, VNA is this Smith chart is used with the VNA in order to verify the performance of RF system and components. So before launching a satellite communication system, that is, engineers test the antennas, cables, and amplifier using a vertical network analyzer. And Smith chart is in order to ensure that is a proper operation. Then oscillator design. Oscillator design, the Smith chart helps to determine the impedance condition required for a stable oscillator operation. That is, for example, in a mobile phone frequency synthesizer, that is RF oscillators generate the carrier frequency, right? So, what is mean by modulation? So, okay. The engineers use the Smith chart to design the feedback and matching networks for the stable oscillation. Then we are going to see about passive IC component. Passive IC component, that is, here we are going to see about RDS. RDS is nothing but drain to source resistance, and mu is the carrier mobility, that is either the electron mobility or hole mobility. Okay. In PN junction diode, the P region, the holes will be the majority carriers, right? So in N region, electrons will be a majority carrier. Okay, mu is the carrier mobility, and COX is the gate oxide capacitance per unit area, and W is the width of MOSFET channel, and L is the length of the MOSFET channel, and VGS is a threshold, that is a gate to source voltage, and VT is the threshold voltage, and VDS is a drain to source voltage. Okay. That is, if the MOSFET operates in a linear region, behaves like a voltage controlled resistor. Okay. Then if it increases VGS, means the RDS to decrease. That is, the MOSFET conducts a more current. Okay. Then we are going to see about passive components used in CMOS circuit. That is, the functions of passive IC component. What are the functions? That is filtering. There are the different types of filters, right? So low pass filter, high pass filter, band pass filter. You have learned about, right? So what is meant by low pass filter? Yes, it filters a high frequency and it allows only a low frequency, right? So the functions of a passive IC component. That is a passive component means that is the resistors, capacitors, inductors. These are the passive component. The passive components are used to remove, that is unwanted frequency components from a signal. That's the main function of filter, right? So high pass filter is it allows only the high frequency, it blocks the low frequency. So that's the main function of passive IC component. For example, in a mobile phone receiver, the filters remove the unwanted noises nearby the frequency and allows only a desired communication channel to pass through. So that benefit is that it improves the signal quality and reduces the interference. That is the main function. And second one is the impedance matching. Impedance matching is that the passive components. The passive components are used to match the impedance between different RF stages in order to maximize the power. Third one is power decoupling. Power decoupling, that is a capacitor. The capacitor is used to suppress the noise and stabilize the power supply voltage. So, in a microprocessor, that is in a microprocessor or a transceiver chip, the decoupling capacitors are placed near the power pins in order to supply the noise and in order to filter the noise and voltage fluctuation. That is the main function of filter, right? So, fourth one is signal conditioning. Signal conditioning is that the passive network modify the signal characteristics such as amplitude, frequency response, and noise levels, right? So, in a real-time example, that is in an audio system, the RF circuits are used to remove the high frequency noises before the amplification. What is the use of amplifier? Amplifier is generally used to amplify the signals, amplify the weak signal, right? So, benefit is that it provides a clean and reliable signal. Okay. That is, in CMOS technology, the passive components such as resistor, capacitors, inductors occupies a significant silicon area. That is a large area or often used to achieve high component values, and it will improve the performance. What are the advantages means? That is better component accuracy, and that is a Q factor, improved the Q factor, and enhanced RF performance. Okay. Let us see the overview. Okay, and that is passive IC components perform filtering, impedance matching, power decoupling, and signal conditioning function. In CMOS technology, the passive components are implemented using a large area layouts, that is a large pixel design, in order to achieve the accurate values of better performance. Then next we are going to see about impedance matching network. Impedance matching network is that it's a circuit designed to minimize the signal reflection and maximize the power transfer between the, that is the source and load. That is in order to maximize, that is in order to equalize the impedance. That is impedance matching. When a source impedance and load impedance are perfectly matched, that means the entire signal will be delivered to the load. However, if there is a mismatch, means the portion of the signal will be reflected back towards the source. That is, the part of the signal will be reflected back to the source instead of being transferred to the load. That is a main issue in a improper matching. Okay. For example, if a mobile phone, that is a RF transmitter, the power amplifier and antenna should be impedance matched in order to ensure the efficient transmission. Without matching, the battery power is wasted and communication quality will be decreased. What are the key benefits? Means it maximizes power transfer and minimizes signal losses. Signal losses will be minimized, and it will improve the system efficiency, and it will enhance the signal quality and range. That is a main um, that is a main important point in impedance matching it. Then signal, then signal integrity. That is, we have already learned about the signal, that is the impedance matching, right? So signal integrity. Signal integrity is nothing but that is the mismatched impedance can causes a signal reflection. That is due to the distortion or reduced signal to noise ratio. What is meant by signal to noise ratio? That is a ratio of signal power to the noise power is a signal to noise ratio. Okay, that is simply we can call it as SNR, right? So impedance matching. Impedance matching minimizes these reflections and improves the signal quality. So then it is reactive power, reactive components. That is impedance matching networks primarily uses inductors and capacitors, right? Which are the reactive components. What is the use of capacitor? It stores the energy rather than dissipating it, right? So next is signal integrity and reactive components in matching circuit. That is we can see the overview. That is signal impedance matching network. Impedance matching network, that is the source and load impedance should be properly matched. Then the signal will be perfectly delivered to the load. That is the main concept. And overview is the signal integrity, and impedance matching minimizes these reflection, and it will be efficiently, the signal will be transmitted to the load itself, right? What are the reactive components? That is the inductors and capacitors. These are the reactive components. Inductance, that what is the main use of inductor? The inductors can store the energy and capacitors also stores the energy, right? So inductors can store the energy in the form of magnetic field and capacitors can store the energy in the form of electric field, right? So unlike the resistors, that is, these components will not dissipate significant power as such, right? So instead, they temporarily store and release the energy, making them highly efficient for impedance transformation. So, what are the what are the advantages of using reactive components? Is that is a low power loss and the efficiency will be high and better signal quality and the maximum power transfer. That is, improve the maximum power transfer and it will reduce the signal reflection, right? That is a main concept of impedance mismatch. Impedance mismatch can cause a signal reflection, distortion, and a reduced SNR. SNR is a signal to noise ratio. Then we are going to see about transformation. Transformation is a impedance transformation and matching network transformation. That is the main purpose of impedance matching is to transform the load impedance so that it appears equal to the source impedance, right? So this is achieved by placing inductors and capacitors in the circuit. So, for example, in a real-time example that is in a Wi-Fi router, that is the LC matching networks are used between RF amplifier and antenna, right? So, in order to ensure the efficient power transfer and strong wireless signals. So, simple matching network. Simple matching network is for example, series capacitor matching, shunt inductor matching. You have learned the second itself, right? So, on a real-time example, that is in a Bluetooth headset. A simple capacitor may be used to match the antenna impedance to the RF transceiver. That is, what are the advantages? Means it is a low cost and the design will be very simple. It is suitable for the single frequency application. So, complex matching network. What is maybe complex matching network is that for broadband application. For broadband application, the requirements that is a more advanced matching networks are used. These networks may include that is a multiple inductor for the simple matching network. We are using a simple inductor or capacitor, right? So for the complex matching circuit, we are using a multiple inductors and multiple capacitors. That is a N network, pi network, T networks. Such these topologies can provide a better matching over a wide range of frequencies. What are the advantages that it is used in a broadband operation? That is a complex matching circuits are used in broadband operation and the performance will be better compared to the simple that is a simple matching network, right? So the efficiency will be very high compared to the simple matching network and it's a flexible design. Okay. Then we are going to see about a common gate amplifier. What is mean by amplifier generally? An amplifier is a used to amplify the weak signal, right? So common gate amplifier, we are going to see about the common gate amplifier. Common gate amplifier is a field effect transistor amplifier configuration. That is, input signal will be fed to the source terminal. The output signal will be taken from a drain terminal, right? Input signal will be given to the source terminal. The output signal will be taken from the drain terminal. That is, the gate terminal is connected to the DC voltage. That is a power supply. It acting as a common terminal for both the input and output. Which terminal? It's a gate terminal will be acting as a common terminal for both the input and output. Generally, the common gate amplifier, that is, it is characterized by the low input impedance, high output impedance, and excellent high frequency performance. Because of these properties, it is widely used in RF and microwave circuits for impedance matching and current amplification. What is the use of amplifier? It's used to amplify the weak signal. Okay. Let us see the characteristics. It's a low input impedance, high output impedance, high voltage gain, and the high frequency response. Okay. Why low input impedance? Since the input is I have already said that the input will be given at the source terminal, right? So, for example, real-time example is that LNA. We have learned about LNA, right? So LNA is nothing but low noise amplifier. In mobile phones, the LNA, that is in RF receiver, the common gate stages are often be used as the input because the antenna and transmission line typically have a low impedance. So that is a common gate amplifier provides good impedance matching and low noise operation. Okay. Another example is a cable TV receiver. Cable TV receiver, that is RF signal. RF signal will be received through the quiet signal, right? So it will be amplified using a high frequency amplifier stages and for the better impedance matching. That is also another example. Now let us see the advantages. Advantages is that excellent high frequency operation and that is a good impedance matching capability and high bandwidth that is suitable for all or RF applications. RF is a radio frequency application. Let us see the disadvantage. Disadvantage is a low input impedance and current gain is very less compared to the common source amplifiers. Right? These are the key features I have already said about. That is, some input signal will be given to the source and output is taken from the drain terminal. And the gate will be heading as a common to both the input and output terminal. Okay? Let us see the application. Application first is current buffering. Current buffering is that is current buffer. The common gate amplifier will be acting as a current buffer. That is transferring current from input to the output with minimal losses. That is, for example, in RF receiver circuit, right? So the CG, that is a common gate amplifier, will buffer the uh, antenna current before they are processed by some certain stages. So benefit is that it prevents a loading effects and it will maintain a signal strength. Second one is impedance matching. That is, due to its low input impedance, the common gate amplifier is ideal for matching the low impedance sources to the high impedance circuits. So, third one is high frequency circuit. High frequency circuit is that the common gate configurations offers very high frequency performance because it is affected by the less affected by the Miller's effect. That is benefit is that it is it gives a performance that is a performance will be better compared to the source common source amplifier, right? So voltage amplification. The fourth one is voltage amplification. That is the voltage. The common gate amplifier provides a voltage gain by converting the input, that is input current variations into the output voltage variations. Benefit is that it amplifies the weak RF signals and it will increase the receiver sensitivity. That is the main benefit. These are the applications of common gate amplifier. Now let us see about the common source amplifier, right? Common source amplifier is a common source amplifier circuit that is similar to the that is CE configuration, CE amplifier model. So the common source amplifier in the MOSFET circuits are similar to the CE amplifier in BJT, that is a bipolar junction transistor circuits. That is both amplifiers, that is a CJ amplifier, sorry, CS amplifier, that is a common source amplifier as well as common emitter amplifier. This both amplifier will provide a high voltage gain and it will amplify the peak signals. It has the similar input and output characteristics. It provides a 180-degree phase shift, that is input and output. Phase shift between input and output. Okay. Students will we have already familiar with common emitter amplifier so that we can easily understand the operations of common source amplifier, right? So you have learned about common emitter amplifier in first year itself, second year EC, that is electronic circuits, you have learned about, right? So, so in a mobile phone, that is an audio amplifier, the common source stage amplifies the audio or RF signal. That is similar to that, only the same operation will be happening in a common emitter amplifier also. That is a common terminal is a common source amplifier. That is input signal will be given to the gate terminal. The output signal will be taken from a drain terminal and source that will be the four terminal, right? What are the terminal? Source, drain, gate, and substrate, right? That is the terminals of yes. Fit. Then we are going to see about the real-time example, that is the FM radio receiver. Okay. Uh, Application is that RF amplifier, audio amplifier, and LNA. LNA is a low noise amplifier that is used in a signal processing circuit. We have learned about, right? Input will be given at the gate, output will be taken at the drain terminal. It will provide a high voltage gain. That is a similar to next slide. That is, it is the common source amplifier is similar to the common emitter amplifier. That is a common terminal is a source terminal is a common terminal. Then it is called as what is called as common source. The common source, the source will be common point for input and output signal. Hence the name is common source, right? Then working principle. Let's see the working principle of MOSFET. That is a MOSFET. MOSFET in a common source amplifier is biased in its saturation region, in order to establish a stable operating point. That is a Q point, quiescent point. Okay. It ensures that the transistors of the transistor that is operates and amplifies both in input, that is a positive and negative variations of the input signal without any distortion, right? So in a real-time example is that in a mobile phone, that is a RF amplifier, the proper biasing, that is, it will keep the MOSFET ready to in order to amplify the incoming signal accurately. Then second one is a small signal amplification. Generally, the amplification is that the amplifier is used to amplify the weak signal, right? So a small time varying AC signal is applied to the gate terminal. The gate controls the channel connectivity. Even a small change in gate voltage causes a corresponding change in drain current. So, in a real-time example is that in a FM radio receiver, that is a weak signal picked up by the antenna receiver, or applied to the gate for MOSFET, it causes some small variations in the drain current. Okay, then voltage amplification. Then voltage amplification is that now, for example, that is it's a small input voltage at the gate produces a large output voltage at the drain. There will be a big difference at the input and output. So this is called a voltage amplification. In a real-time example, in an audio amplifier, the small microphone signal is amplified into a large voltage signal capable of driving a subsequent status. That is from the heat stage, the signal will be amplified and it will be received at the receiver. That is a voltage amplification. So let us see the overview. MOSFET is biased in saturation region, that is a Q point. The small AC signal is applied to the gate. The gate voltage variation changes the drain current. Gate voltage changes the drain current, and drain current variation produces large voltage across the drain resistor. That is, amplified output voltage will be happening as a drain term. Okay. This is the overview, and let us see into the open circuit time constant. Open circuit time constant, that is a OCTC method. It's also called as zero value time constant, that is ZVTC method. It's also called zero value time constant method. It's a powerful circuit analysis technique. It's used to estimate, that is upper cutoff frequency, dominant pole, bandwidth of amplifiers and electronic circuits. This method is especially useful because it simplifies the analysis of complex circuit. If the complex circuit is this method is used to analyze a complex circuit containing, that is, multiple capacitors, multiple inductors without requiring a lengthy mathematical calculation. That is similar to that of a Smith chart. The Smith chart is used to find out in order to avoid the lengthy calculations used to find the impedance and admittance, right? So this is also a simplifies, that is OCTC method. It simplifies the lengthy calculation. Let's use it to analyze the complex circuit. The basic principle is that if you consider one capacitor at a time, we have to open circuit all other capacitor. So it will be very easy to calculate the value of that capacitor. And from the capacitor value, we can find out the time constant. That is tau equal to R. Tau is the time constant, R is the resistor value, and C is the capacitor value. Why it is important means it's used to calculate the amplifier bandwidth quickly, and it identifies the dominant pole, and it simplifies the high frequency amplifier design. It reduces the complex calculations, and it is widely used in RF and analog circuit design. Okay, let us see about the key aspects of open circuit. That is the dominant pole and the individual time constant OCTC method. That is the open circuit time constant method. That is the dominant pole is a pole that has the greatest effect on frequency response of the circuit. Dominant pole is the greatest effect on the frequency response of the circuit. That is the frequency that is a frequency at which amplifier gain will be decreased at the rate of minus 20 dB per decade. Yeah. Then individual time constant. Individual time constant is used to it simplifies analysis by considering one capacitor at a time. I have already told that tau equal to RC. From that, we have to calculate the time constant value, and either time constant value or either we have to find out the resistance value, right? Then it will be very useful. So bandwidth estimation. Bandwidth estimation is that one of the main advantages of OCTC method is that it provides a simple and efficient way in order to calculate the up to minus 3 dB frequency of the circuit. That is, a 3 dB frequency is a frequency at which amplifier gain drops to 70% of its maximum value. Okay. Second one is intuition about circuit behavior. Another important benefit of OCTC method is that it helps the engineers, that is, in order to develop intuition about which capacitors have a greatest effect on frequency, circuit frequency response. By calculating the tau equal to RC, that is, it becomes clear which capacitor contributes the most to the bandwidth limitation. That is, if it is have a larger time constant, that is, it has a great impact on bandwidth, and if it has a smaller time constant, it has a lesser effective on less impact on the bandwidth. This helps the designers focus on the critical capacitors in optimizing the amplifier performance. That is the main concept here. And let us see about high frequency amplifier design. High frequency amplifier design, that is, it is mainly focused on amplifying the signals at RF and microwave frequency while maintaining the high gain, wide bandwidth, and low noise at stable operation. These are the main constraints of high frequency amplifier design. Then we have to go. Let us see about the key considerations of high frequency amplifier design. That is the impedance matching. That is the input and output impedance must be properly matched in order to ensure that there's a maximum power transfer and minimal signal losses. Okay. Next one is managing the parasitic effects. Managing parasitic effects that we have to, that is, every transistor contains some unwanted parasitic capacitance and resistance that will limit the bandwidth and reduces the gain in high frequency. Okay. Next is stability. Stability is that is an amplifier must detect, that is must remind a stable and unwanted oscillations over a particular rated frequency range. That is, for example, in a satellite communication receiver, that is, instability can cause self-oscillation, and it will cause an interference with the signal reception, right? So stability analysis ensures a reliable operation. Then let us think about the LND. LND is nothing but low noise amplifier. Low noise amplifier is a low noise, that is a noise matching. The noise matching in low noise amplifier, that is in a RF amplifier design, especially in the low noise amplifier, there will be the two main objectives are considered. What are the means? That is a power matching and noise matching. Power matching is that it will maximize the power transfer from the source to the amplifier. Then that is second one is noise matching. First one is power matching, and second one is a noise matching, right? So noise matching, it will minimize the noise matching. It will minimize the amplifier noise figure. That is a noise. Noise figure is that we can simply call it as N. These are the main objectives, but it is different. And designers must be used to find a suitable trade-off between it, right? So noise matching is a process of selecting the input impedance of the amplifier so that noise, that is a noise figure is minimized. Why the noise matching is important? Many communication systems, that is, many communication systems receive extremely weak signal, right? So, if the first amplifier adds a excessive noise, the original information may become very difficult to recover original information, right? So, therefore, the first stage of receiver is usually designed for minimum noise rather than maximum power transfer. We have to consider the minimum noise rather than maximum power transfer. Okay. That is the main motto of while designing the circuit. That is, in a real-time example is that is in a GPS receiver. That is, GPS satellite signal reaches a smartphone at a very low power level. The signal strength is extremely weak. So, an additional noise can corrupt the signal. So, LNA is a low noise amplifier. Thus, masked to achieve the low possible noise figure. Result is that it will it, that is will get a better location accuracy வந்துட்டு better கிடைக்கும். So in order to improve the satellite, that is signal reception ஓட signals வந்துட்டு improved ஆகும். Let us see the um, that is the difference between noise matching and power matching. Or let us see the difference. Okay. Noise matching and power matching. That is a noise matching, it will minimize the noise figure, and a power matching, it will maximize the power transfer. The word itself we have to consider. That is minimal minimal noise figure and maximizes the power transfer. And in noise matching, it will improve the receiver sensitivity. அங்க வந்துட்டு power matching it will increase the signal power. Yeah. இங்க பாத்தீங்கன்னா இப்ப noise matching வந்துட்டு we are going to focus mainly on signal quality. அங்க பாத்தீங்கன்னா it mainly, that is power matching பாத்தீங்கன்னா it will mainly focus on a signal strength. That is the main difference. Yes, I have already told that. That is noise matching. This is the difference, noise matching and power matching. Let us see the relationship between noise and power matching. That is trade-off between noise matching and power matching. In a low noise amplifier, that is the source impedance that gives the minimum noise figure, right? So usually different from the source impedance, and it provides a maximum power transfer. This will create a trade-off between noise performance and power transfer efficiency. Why this trade-off of that? So the noise matching requires a source impedance to be equal to the maximum noise impedance or reflection coefficient. That is the so power matching so அது வந்து ரெண்டுமே வந்துட்டு they will not be equal. So both condition cannot usually be satisfied at the same time. So real-time example, the phone, that is a mobile phone receiver. So in a 5G smartphone receiver, the incoming signal from the antenna is very weak. So engineers have to prioritize. என்ன prioritize பண்ணணும் அப்படின்னா first வந்துட்டு power matching, that is more power enters the amplifier but additional noise may be introduced. Noise matching வந்துட்டு that is less noise is added and it will improve the receiver sensitivity. A result. What is the result of that is the better call quality and improve the data reception. That is a higher receiver sensitivity. These are the results we are going to get while designing a perfect LNA. Then what we have to consider while designing the LNA? That is, I have already told that same concept is same here. That is, source impedance provides a minimal noise figure that is usually different from the source impedance, and that provides a maximum power transfer. That is a main. That is a the same concept is the same. That is, LNA and receivers prefer the noise matching, and power amplifiers and transmitters prefers the power matching. That is the main concept. Noise matching, power matching. Noise matching the பார்த்தீங்கன்னா வந்துட்டு that is, it will it will prefer the noise figure. அதுதான் மெயின் ஃபோக்கஸ். இங்க பாத்தீங்கன்னா வந்துட்டு மேக்ஸிமம் பவர் டிரான்ஸ்ஃபருக்கு மினிமல் நாய்ஸ் ஃபிகர் வந்துட்டு நாய்ஸ் மேட்ச். அங்க வந்துட்டு மேக்ஸிமம் power transfer. That is the main concept in power matching. And let us see about a single-ended and differential LNA. Single-ended differential LNA அப்படின்னா, that is, there will be the two architecture. என்னென்ன அப்படின்னு, first one is single-ended LNA and second one is differential LNA. Single-ended LNA அப்படின்னா, the signal is applied to the one input terminal with reference to the ground. That is, let us see the characteristics of single-ended LNA. That is, the circuit will be very simple and it consumes a very low power. The chip area will be small and it's easy to design. These are the main constraints. Okay? These are the main features. For a differential LNA, the signal is carried on two complementary paths. The amplifier processes a difference between the two signals. Yeah. It will be, that is a single LNA பார்த்தீங்கன்னா வந்துட்டு, that is, the signal will be applied to one terminal itself with reference to the ground. But in a differential LNA, the signal will be carried on two complementary paths. So the amplifier process is to a difference between the two signals. Let us see the characteristics. That is, it provides a better noise immunity and it improves the linearity and it will give the better performance at high frequency. Okay. This is a common mode rejection. Common mode rejection is, that is, a common mode noise is a noise that appears equally on both the signal line and grounded reference. At the signal line or the reference ground layer, that is a common mode noise. Since a single-ended LNA process only a single path, it cannot be effectively cancel this noise. But differential LNA, it will be cancelled. Let us see the advanced application. The single-ended LNA are mostly suitable when a low cost is important. Simplicity, that is, circuit will be very simple. The power consumption will be very minimal. The noise is not a major concern. We can use it as we can use a single-ended LNA. That is, we are using it in FM radio receiver, basic wireless receiver, simple RF module. We are using a single-ended LNA. Differential LNA, that is, the signal will be carried along two complementary paths and they have equal amplitude but opposite polarity. Amplifier that will process the difference between two signals. Yeah, that is the main concept here. And why it is used again? First, differential LNA or an ideal for applications where high noise immunity is required. That is, so high noise immunity is required and signal integrity is critical. High speed communications is involved, and we are going to use a differential LNA. For example, where we are using a differential LNA, that is 5G or 4G mobile phones, Wi-Fi routers, GPS receiver, radar system, satellite communication system. We are using a differential. Last one is the features of single-ended LNA and differential. That is, signal handling. that is a single input signal. இங்க வந்துட்டு two complementary path, that is a differential linear. We are using a two complementary path, and amplifier will process the difference between those signal, right? இங்க வந்து cost வந்துட்டு it will be lower, இங்க வந்துட்டு higher ஆ இருக்கும். Noise வந்துட்டு இங்க வந்து lower ஆ இருக்கும், இங்க வந்துட்டு it will be higher. Common mode rejection பார்த்தீங்கன்னா that is it will be lower, இங்க வந்துட்டு higher. So these are the application. Thank you.